sklearn, model selection, crossval predict. Description. Crossval predict is a function within scikit-learn sklearn that provides a convenient way to perform cross-validation and generate predictions on the same data. It is particularly useful for understanding the generalization performance of a machine learning model without the need to separate the data into distinct training and testing sets. Inputs. Estimator. This is the machine learning model you want to evaluate. It should be an instance of a class from scikit-learn's model selection module. Example: logistic regression, random forest classifier, etc. X. This is your input feature matrix. It should be a 2D array where each row represents a data point and each column represents a feature. Y. This is the target variable or labels. It should be a 1D array with the same length as the number of data points in X. This can be a continuous variable for regression models or a categorical variable for classification models. CV. This specifies the cross-validation strategy. It can be an integer, specifying the number of folds in a standard k-fold cross-validation. Or it can be an instance of a cross-validation generator from scikit-learn. This determines how the data is divided into training and validation sets during the cross-validation process. Method optional. This parameter allows you to choose the prediction strategy. The default is predict, which predicts using the trained model. Alternatively, you can use predict proba for probabilities in classification or decision function for scores in classification. Outputs. YPRED. This is a 1D array containing the predictions for all the data points in X. The predictions are made based on the cross-validation process, using each data point in a validation set and predicting on it with the model trained on the remaining folds. The format of the output depends on the type of model and the method parameter. CV results. This parameter is optional and not always used. If you set return train score true, it provides a dictionary with the scores for each fold and each metric you specified. This helps you analyze the performance of the model during the cross-validation process. Steps. Data splitting. The function first splits the data X and Y into multiple folds according to the specified cross-validation strategy. This is handled internally and based on the CV parameter. Model training and prediction for each fold. The function trains the estimator on the data in the remaining folds and then makes predictions on the data in the current fold. This process is repeated for all folds. Prediction aggregation. Finally, the function aggregates the predictions made on each fold to create a single array of predictions. YPRED for all data points in the input dataset. Metrics. Accuracy for classification models measures the proportion of correctly classified instances. Accuracy is often used for imbalanced datasets where the number of instances in each class is very different. Precision for classification models measures the proportion of correctly predicted positive instances among all predicted positive instances. It is useful when the cost of false positives is high. Recall for classification models measures the proportion of correctly predicted positive instances among all actual positive instances. It is useful when the cost of false negatives is high. F1 score for classification models. The harmonic mean of precision and recall provides a balanced measure of both precision and recall. R-squared for regression models measures the proportion of variance in the target variable explained by the model. A higher R-squared indicates a better fit. Mean squared error MSE for regression models measures the average squared difference between the predicted and actual values. A lower MSE indicates a better fit. Visualization plots. Confusion matrix, a visual representation of the performance of a classification model. It shows the number of true positives, true negatives, false positives, and false negatives, useful for understanding the model's ability to differentiate between classes. Precision recall curve shows the trade-off between precision and recall at different thresholds. Useful for understanding the performance of the model at different levels of confidence. ROC curve plots the true positive rate against the false positive rate at various thresholds. Useful for evaluating the model's ability to discriminate between classes. Residual plots for regression models plots the difference between the predicted and actual values. Useful for identifying patterns in the errors and assessing the model's fit. Fine-tune parameters. CV experimenting with different cross-validation strategies, e.g. K-fold, stratified K-fold. Leave one out to find the best approach for your data and model. NJobs set this parameter to a positive integer to use parallel processing for faster execution. The value determines the number of cores to use. Method if needed. Use predict_proba or decision function to obtain probabilities or scores, respectively. For more detailed analysis, uncertainty methods. Confidence intervals by performing cross-validation with different random splits. You can estimate confidence intervals for your performance metrics, providing an indication of the uncertainty in the model's performance. Bootstrap aggregation bagging, combining predictions from multiple models trained on different subsets of the data can help to reduce variance and provide a more robust estimate of the models. Uncertainty. Challenges and fixes. Challenge 1: data leakage. If your data has time-dependent features, splitting the data randomly into folds can lead to data leakage, where information from the future is used to train the model. This can result in overly optimistic performance estimates. Sample use case that resulted in challenge 1: imagine you are predicting stock prices based on historical data. If you split the data randomly into folds, information about future stock prices might be included in the training data for a fold, leading to an unrealistic performance evaluation. Fixes to challenge 1: use time series cross-validation strategies that ensure data from the future is not used for training. For example, a rolling window approach where the training data consists of a fixed window of historical data. Challenge 2: class imbalance. If your data has a significant class imbalance, e.g. many instances of one class and very few of another, standard cross-validation can lead to biased performance estimates. The model may become overly focused on the majority class and perform poorly on the minority class. Sample use case that resulted in challenge 2: imagine you are building a fraud detection model. Fraudulent transactions are likely to be rare compared to legitimate transactions. If your data is highly imbalanced, the model might overfit to the majority class legitimate transactions and perform poorly at identifying fraud. Fixes to challenge 2: use stratified cross-validation to ensure that each fold contains a similar proportion of instances from each class. Consider oversampling the minority class or undersampling the majority class to balance the dataset. Challenge 3: computational complexity. Performing cross-validation can be computationally expensive, especially for large datasets or complex models. The complexity can increase significantly with the number of folds and the size of the dataset. Sample use case that resulted in challenge 3: you have a dataset with millions of data points in a deep learning model. Performing 5-fold cross-validation might take a significant amount of time to complete. Fixes to challenge 3: reduce the number of folds, e.g. use 3-fold or 2-fold. Consider using parallel processing NJobs parameter to speed up the cross-validation process. Explore efficient implementations of your model or cross-validation strategy to reduce computational cost. Experiment with using a smaller subset of your data for cross-validation, especially during the early stages of model development.